Okay, so our final for my Monday, Wednesday, Friday, 10 a.m. class is Monday, May 11th from 11 a.m. to 12:50 p.m. in here. If you wanted to take your final exam at a different time, you need to email me so I can make sure I can double check that I don't have too many people trying to show up to the same final exam time slot. Some of my rooms have only a limited number of free seats. All right, so the final is 17 questions. It's split about half and half for multiple choice versus free response. Mm. Sorry. Could not get to sleep last night. I am groggy. So I'm just trying to pull it up so I can count how many questions. But if anyone has a webwork problem that they want to start on, 8 multiple choice, 9 free response. So on the multiple choice, if you pick the right answer randomly out of the blue, you'll get full credit. So as long as you're confident in your answer, you don't have to show work. If you're not confident in your answer, then you should show work so you can get some partial credit in case you pick the wrong one. So it depends on the problem. So for some of them, you can very confidently get the right answer without showing any work, and I'm fine with that. Or just showing like scratch work that may not be like logically coherent, but it makes sense to get you to the answer. So who's got a number from the webwork practice problems that they'd like to see worked? All right, so here's what I have for problem 9. We're told that the tangent of theta is 2 and that theta is between 0 and pi over 2. And we're asked to find sine 2 theta and cosine 2 theta. Now on the test, you'll only have to do one of those, but the angle won't be in quadrant 1. It'll be somewhere else. You actually have to deal with the negative. Like deciding if you should use a negative for one of the sides or not. But starting it out, they go to the effort to tell us it's in quadrant 1. 0 to pi over 2, 0 is the positive x-axis, pi over 2 is the positive y-axis. So in between those two is somewhere in quadrant 1. There's our theta. So when we're told the tangent of theta is 2, well, we got to remember what we know about tangent. So when I've drawn an actual right triangle, then this should come back to labeling sides of the triangle, and tangent is 2 of those sides of the triangle. So what do we call the sides of the triangle? What do we call the diagonal side? Yep, there's our hypotenuse. What do we call the vertical side? Yep, our angle is always on the origin, so the vertical side is opposite. And then the horizontal side has to be adjacent. Now, tangent is what over what? So this is our hippies. So we have some old hippie caught another hippie tripping on acid. So tangent OA. But our 2 doesn't have an over. So we're going to sneak back in at over 1. So this means our opposite side is 2. Our adjacent side is 1. And we got to figure out the hypotenuse. So I'm going to call that C. Because our good old Pythagorean theorem, a squared plus b squared equals c squared. So this is 1 plus 4. So we have 5. C squared is 5. So we square root. Anytime we square root, we remember that plus or minus. But hypotenuse is always positive. Plus we're in quadrant 1. Everything's positive. All right. So now that I've drawn my triangle, I can fill out what the sine of theta and the cosine of theta are, because I'm going to need those for my double angle. So sine opposite 2 over hypotenuse square root of 5, cosine 1 over square root of 5. So now that I've done my triangle setup, I know what my sine and my cosine are. Now I can look up my formulas for sine 2 theta and cosine 2 theta. Now sine 2 theta only has one formula. 2 times sine theta times cosine theta. Now, since I know sine theta is the same as 2 over the square root of 5, in place of sine theta, I can write 2 over the square root of 5. Note, I am not writing 2 over the square root of 5 as theta. That is not theta. I don't know what theta is here. It's some angle. But 2 over the square root of 5 is what the sine of theta is. Similarly, cosine of theta is 1 over the square root of 5. So now I just finished the calculation. That's 2 over 1. 2 times 2 times 1 is 4. 1 times the square root of 5 times the square root of 5 is 5. So we get 4/5 for our sine 2 theta. All right, now cosine 2 theta has extra formulas. But the first one is cosine squared theta minus sine squared theta. That's usually the one I go with because I've done the triangle. I already know what sine and cosine are. So cosine squared, that's 1 over the square root of 5 squared minus, and then sine squared is 2 over the square root of 5 squared. So I end up with 1/5 minus 4/5 gives me -3/5. So there's my two answers for web work. All right, problem 12 is a little word problem. So a satellite calculates the distances A kilometers, B kilometers, and the angle gamma in degrees as seen in the figure below, not to scale. If A is 397 kilometers, B is 363 kilometers, and gamma is 2.9 degrees, find the distance between the two cities. So this one is very directive because it's labeling everything for us. On the test, I'm going to give you the numbers and an angle, and I'm going to give you a diagram with the numbers filled into the diagram. So it's going to look more like, so I'll write the 2.9 degrees there, 397 kilometers, 363 kilometers. So we need to label the triangle with A, B, and C and alpha, beta, gamma. Now there's two formulas we can use here. There's law of sines, which is sine alpha over A equals sine beta over B equals sine gamma over C, or we have our law of cosines. C squared equals A squared plus B squared minus 2AB cosine gamma. So when I'm only given one angle, I like to call that angle gamma, because I only give you guys this one version of the law of cosines. So if I've decided to call this 2.9 degrees gamma, then which side is C? Is it the 397, the 363, or the third side? Yep. C has to be opposite angle gamma. So if I've called that angle I'm given gamma, C has to be this opposite side. Now I got to fill in A and B. Now it doesn't matter which one I call A and B, the two sides are like interchangeable at this point. So I usually just call the one on the left A and the one on the right B, but it truly doesn't matter. Now, if I look at law of sines, I know side A, side B, and angle gamma, but I don't know alpha, I don't know beta, and I don't know side C. So I need 3 of the 4 pieces between 2 fractions in order to use law of sines. I only know 1 piece from each fraction for law of sines, so law of sines is not going to help me solve here. But my law of cosines, I know A, I know B, and I know gamma. That's everything on one side of the equation, so I can solve this. So we'll have C squared equals 397 squared plus 363 squared minus 2 times 397 times 363 times the cosine of 2.9 degrees. So we better make sure our calculator is in degrees mode. All right, now over to the trusty calculator, 397 squared plus 363 squared minus 2 times 397 times 363 times the cosine of 2.9. I get 1,525.1094, blah, blah, blah. All right, what are we forgetting? Yep. This is c squared. I need to square root it. So I raise that answer to the 0.5 power, and it gives me a c of 39.0526. It didn't give us rounding directions, so whatever you want. So 39.05 is good. And if we look at the triangle, like 39 seems pretty small, but I look at that 2.9 degrees, that also seems really small. So 2.9 degrees is a very tiny angle. The side opposite that should be very tiny. So even though 39 feels very small, it's going with a very small angle. So this is okay. The 1525 we got was too big. There's no way 397 and 363 can bridge a 1,500 kilometer gap. So even though 1,500 might make more sense on the scale of distance between cities, looks like they were measuring neighborhoods of San Antonio here instead. All right, this one is multiple choice. I did try to make it so if you did the calculation in radians instead of degrees, that the radian answer was not one of the multiple choice answers. So if you do the work and your answer isn't matching, make sure your calculator is in the correct mode. I didn't necessarily work that hard on the answers on all of them, but at least on this one, I was a little more careful about the wrong answer choices. Now that 1525 though might be a wrong answer. So you do need to think about, is my answer too big? Does it make sense? All right, what's another one we can take a look at? So 16 and 17 are about the log properties. So I am not going to give you the list of log properties. You do have to remember how these work together. But I'm only going to ask one question on this. So it's either an expand or a compress. So problem 16 is a log property expansion question. And then problem 17 here is a compression, condense, zip them back all up into one log. So A here, I've just got two terms. 9 times the log of x plus 8 times the log of x plus 6. So if I'm going to put these back together, before I can use my plus rule for logs, I need to move my powers back up. So this becomes the log of x to the 9th plus the log of x plus 6 to the 8th. Now I can actually use my rule for when I have log A plus log B. I can zip that back together as a single logarithm, and I multiply the results. So x to the 9th times x plus 6 to the 8th. That does not simplify anymore. Like theoretically, we could multiply x plus 6 times itself 8 times, but please don't. The directions were to write it as a single logarithm. That is a single logarithm. The answer that we would type in the blank is just what's inside the log. So x to the 9th times x plus 6 to the 8th. All right, now our other one, we have log of x minus 3/2 log of y plus 7 log of z. So log's whole purpose in life is to take powers and bring them down. But when we're compressing logarithms together, our first step is to put the powers back up. So I'm still going to have log of x because there was no power in front of the x. Now you could move this as a negative 3/2 for the y power and then just leave it as a plus. I usually leave the minus. But either way works. All right, now I no longer have coefficients in front, so I've got log of thing minus log of other thing plus log of third thing. So that minus tells me I'm going to write these two as a single logarithm. I'll have the first thing x divided by the second thing y to the 3/2. All right, and then my plus tells me that I'm going to multiply these two results. So it'll be one single logarithm, x over y to the 3/2 times z to the 7th. So you can write it like this, where the z to the 7th is next to the fraction. But if we cleaned this up, that z to the 7th would multiply on top of the fraction. So it'd be the log of x times z to the 7th, all divided by y to the 3/2. Now, you don't have to show that many steps of work. In fact, I have some people who can look at that result and skip straight to the answer, and that's perfectly fine. So if you've done logs before, or you did a lot of practice with them and you're very comfortable with your log properties, totally fine if you can skip straight to the answer. I would appreciate one line of work in between. So I'll usually do like, I move my powers up, and then I'll very often after that go to the last line. Like I'll do the whole combining as one step. So that's using our log properties to zip a logarithm back up, or zip several logarithms back up into a single logarithm. Now, these are the same properties we have to use when we're solving log equations. So I don't think I've done problem 20. So let me grab that one real quick. Like 19 and 20 are very similar. And I know I've done 19 in a video. I just haven't done 20 yet. So I'm grabbing that one because it's good practice. So we have log base 4 of x minus 5 equals 2 minus log base 4 of x minus 11. So we are solving an equation. We are finding values of x that will work in this entire equation and to make the entire equation true. So there are some numbers that if I plug them in, they're going to give me bad math. Like if I plugged in x equals 0, 0 minus 5 is negative 5. I can't take the log of negative number. So the first inequality actually tells me that my x values have to be bigger than 5. Sorry, the first logarithm domain. The second logarithm domain tells me x minus 11 is positive, so x has to be bigger than 11. So if I get a solution where my x value is smaller than 11, I'm going to throw it out. But if you don't notice that at first, you can also notice it by checking your results at the end. Now, in order to solve this equation, I need my logarithms on the same side so I can use my log properties to combine them. So I'm going to add the logarithm to the other side. Now, logarithms do not add normally, so we're not just going to add the insides and call it good. I'm going to rewrite this one logarithm plus another logarithm. And this is equal to 2. So when I add two logarithms with the same base, I can combine it into a single logarithm, so it'll still be log base 4. But then I'm going to multiply the inside, so it'll be x minus 5 times x minus 11. And that's all inside the logarithm. Now that it's a single logarithm, log of thing equals a number, now I can use my inverse operations to unlock the log base 4. So what undoes, what gets rid of log base 4? Yep. So when we say power of 4, do I mean raise both sides to the 4th power? Yeah, the other way around. So the 4 base. So 4 caret on both sides. Like that's the way I've been symbolically writing it. So my inside result, x minus 5 times x minus 11, now equals 4 to the 2nd power is 16. So I did a whole bunch of work to end up with a quadratic equation. Now, at this step, it is so tempting to be like, oh, I can just do x minus 5 equals 16 or x minus 11 equals 16. No, that is not the way solving quadratics work. We can only set the binomials equal to 0. Now, this does not mean do x minus 5 equals 0 and x minus 11 equals 0. We can only do that when the other side of the equation is 0. Right now, that 16 is a big problem. So we need to multiply these two things out and then minus the 16 over so it's equal to 0. So we're going to have x squared minus 11x minus 5x plus 55 is equal to 16. So I have x squared minus 11 and minus 5 is minus 16x's. And then 55 minus 16 gives us plus 39. So now I've got a quadratic that is equal to 0. Now I can factor or I can use the quadratic formula. I don't have the quadratic formula written on the formula sheet, but if you want to use it and you don't remember it perfectly, come up and ask me and I will write it down for you. No problem. But 39, there's not a lot of numbers that multiply to 39. So 39 is divisible by 3, and it turns out it's actually 3 times 13. And there we go. 3 plus 13 would be 16, but I want negative 16, so I make both of them negative. Now, because I have a product equal to 0, one of these two pieces of the product must be 0. Either x minus 3 is 0 or x minus 13 is 0. This is a very special fact of 0. The only way to get a product to equal 0 is if one of the two pieces is 0. Earlier, when I had 16, it could be 2 and 8. It could be 4 and 4. It could be 32 and a half. It could be negative numbers. Like, there's way too many ways I can multiply stuff and get 16. But multiplying stuff to equal 0, one of those two pieces has to be 0. I don't know which piece, so I set them both equal to 0, and I solve. Add 3, add 13. So I have two potential solutions. Now, when you're finishing a log equation, because logs have restricted domains, check your answer. Or go back and check the domain restriction. So if I take my original equation, and I go back and substitute in x equals 3, I get log base 4 of 3 minus 5. That is log base 4 of negative 2. That is enough to throw out x equals 3. I can't take the log of a negative number. Even if only one of the logarithms is a negative number, that's enough to throw that answer out. It cannot be 3. Now our 13 13 minus 5 is 8. 13 minus 11 is 2. I can do log base 4 of 8. I can do log base 4 of 2. They're not pretty numbers. They're ugly decimals, but they're real numbers. So that means the only solution to this equation is x equals 13. Now, webwork doesn't have a lot of practice problems for this. Like the show me another button doesn't work. It just didn't program in extra versions of this question. I think 19 has a few extra versions though. You can also, if you go to this section 6.4 in the online textbook and scroll to the bottom of the section, it's got a whole bunch of questions, practice questions you can work. So just scroll until you see equations where you've got multiple logarithms. Those should be the ones that'll produce a quadratic where you have to do all this work. Mhm. When we're solving equations, they're always the same base. Like it's not impossible to get an equation with different bases, but it's really rare. Like usually we will go out of our way and just write everything in terms of base E. Just because in calculus, log base E has some really nice properties and the e to the x has some really nice properties that we exploit. So yeah. That's actually why like in calculus, when you're doing carbon dating, most of the other science textbooks will use everything in terms of base E, just because that's the most common base. It's on the calculators and it's just natural to write equations in terms of E. Like the only exception is the pH formula in chemistry, just because the pH system is base 10. All right, so this is one of the 10-point problems on the test. All right, what's another one from the list y'all want to look at? Yeah. Been a while since we did one of these. So finding the inverse of a function. So when they explicitly ask you to find the inverse, this is where we would do the swap x and y and then solve for y. The algebra on them is weird, but you are going to use these algebra skills in calculus. That's why I kept putting why it was on the test and why it's on the final. So f of x equals x over x plus 1. So my first step is I'm going to write y in place of the f of x. So y equals x over x plus 1. Now I'm going to do my swap. So everywhere there's a y, I write an x. Everywhere there's an x, I write a y. So now I have x equals y over y plus 1. Now my whole goal is to get y by itself. Now, not just by itself, but that there's only one instance of y in the equation, and that instance is by itself. Right now, there's two y's. So solving this is going to be a little more annoying. But this is an equation with a fraction. Fractions are horrible. So the first thing we want to do is multiply to get rid of that fraction. So what am I going to multiply by? Yep. We're multiplying by what we're dividing by. We're dividing by y plus 1, so we multiply by y plus 1. So that way over here, y plus 1 and y plus 1 will cancel each other out. So I'm left with just a y. And then on the other side, I have x times y plus 1. I have my parentheses there. So the parentheses remind me I need to distribute. If you don't write your parentheses, it'll just look like y plus 1 times x, and you'll just write y plus x, and then the whole equation, wrong. So we have xy plus x. Now we want to get y by itself. I have more than one y in my equation right now. So my next step is to get everything that has a y on the same side. So I'm going to minus xy from both sides of the equation. Now, if you prefer to keep your y's on the left, you can minus the y and minus the x, like trade out the two terms. I just do it this way because it's a little less steps. So now I have x equals y minus xy. Now, both of these terms, I put them on the same side because they both have a y. So if I write that common y, factor it out, then y times, I need a 1 as a placeholder. So if I distributed back, y times 1 would get me back to y. Minus, my y is out front, so I need an x. So that way y times x is xy. Now our last step, I want to get y by itself. Y is currently being multiplied by a weird mess. So I want to divide by the weird mess. So now our inverse function, y is x over 1 minus x. And I can trade this out for f inverse of x. So that is our result. But if we solved it a different way, we could also get negative x over x minus 1, and that is also an acceptable answer. So if you did the solving a slightly different way, you'd end up with that slightly different answer, but both are correct. So this one is actually multiple choice. So theoretically, you could take the answer and compose it with the provided function, and everything would cancel out and you'd get x for the inverse. But composing the two functions together is more work than doing this, because you've got 4 answers to check. So all right, what's one more you guys want to take a look at real quick? All right, so 18 is solving an ugly looking exponential equation. I say ugly looking, not because the numbers themselves are ugly. So 2 to the 4x plus 3 equals 3. But because there is no way to write 2 in terms of 3 or 3 in terms of 2 here. So we are stuck using a log on both sides. Now, the directions here specifically say type an exact solution in terms of natural logarithms. So we need to use the natural logarithm on both sides. So the natural log of 2 to a power, log's power rule still comes into play. So that's going to bring that 4x plus 3 in front of the natural log 2. Now this natural log 2 is a number. I can multiply this number through. So I have 4x natural log of 2 plus 3 natural log of 2 equals the natural log of 3. And now I'm trying to get x by itself. There's only one x. So before I can get rid of the stuff smushed on the x, I need to get rid of this extra term that's being added. So I'm going to subtract 3 natural logs of 2. So I have 4x natural log of 2 equals the natural log of 3 minus 3 natural log of 2. And then this x is smushed in here, so that 4 and that natural log 2 are both being multiplied to x, so I can divide them out. So our final solution is the very weird looking natural log of 3 minus 3 natural logs of 2, all divided by 4 natural logs of 2. The natural logs of 2 do not cancel there because my overall operation on top is a minus. In order to cancel that natural log of 2, I'd have to factor it out of the top, and it doesn't factor out of natural log of 3 nicely. So that horrible thing is our solution. That is the exact solution in terms of natural logs. Now, if looking at the equation in terms of natural logs like kind of messes with your brain and you want to write down what the decimal for natural log 2 and the decimal for natural log 3 is, and then just work the equation with the decimals, you can do it that way. But for web work, you actually need to write the answer in terms of the natural logs. We are right at time, 10:50 on the dot.